So I guess I'll start. So I don't know how many of you have experience with VHDL. Okay, but, so about half. The story. So hi, my name is Henrik Eekhout, and I'm one of the founders of Sigasi. And today I'm going to talk about how I came to found Sigasi, the company that builds an Eclipse product. So first I'm going to tell about why and what we do, and next I'll relate about our approach and some of the difficulties we ran into making a company that builds on Eclipse tools. So my story with Eclipse begins about 8 years ago while I was pursuing my PhD, and my PhD topic was scalable video coding. And for this PhD, I did both research in hardware implementations, and I also had to do software development. So on Monday, I had to write software, and it was in Java. And the first time I started using Eclipse was like, wow, what a godsend. This tool really helps me focus on the creative part and all the ugly stuff it can do for me, so I could very easily navigate around in my code. I could simply hit Ctrl space to see the fields of an object, or if I made a stupid mistake, I knew it within the keystroke. And if I made a mistake, the tool most of the time can fix my problem and rename, extract methods, all those things that you're familiar with, or really enhance my productivity. So imagine the pain I felt when the next day I had to write VHDL, and the best tools available at that time were VI and Emacs. So no automatic navigation, so it was grep or some other text find methods. No autocomplete, so every VHDL designer I know has this tiny syntax guide next to his desk, like, oh yes, configuration, how is the syntax again. Also no real-time errors, it's type for a bit, run it through the compiler, scroll to the logs, go back to your file, so it was a real productivity killer. Also, if you know there's an error and the compiler says it's on line 5, you have to look around line 5 to find something in your code, so you're staring and staring. Also, no refactoring support, so most of the time you simply live with the wrong variable name choice, and in the end you get very ugly code. So what we needed was what we experienced with Java we wanted also to have for VHDL. So my PhD was on scalable video coding and VHDL, and I didn't have time at that point to create a new tool, but by the end of our PhD we were wondering like what will we do next, and so the idea came more like if nobody else is doing it, we will have to do it, and that's our opportunity to make a dent in the universe. So the question we ask ourselves, can we fix this? So the answer is yes, we can. But how? So together with a colleague at the university, we decided, okay, we will do this, but how can you, with two guys, make a commercial quality? So electronic design automation is like the common denominator for tooling in the chip business. So how can we make a tool? And so we had lots of questions. So not only technical questions, but also like business questions like, do we stay at university and work on this first, or do we start a company immediately? But we had no experience at all with companies, so there were lots of difficult questions. And so for the technical part, we were very lucky that Eclipse is a lot more than just JDT. So Eclipse, all is open, you all know it, so it allows you to extend it with your own plugins, so you can focus on the VHDL specific part, and everything else you can reuse from other projects. So that was extremely helpful for us to get started. So before I go further into how we did it story, first for the other half of the public who is not familiar with VHDL, first some background information. So VHDL is an acronym, and so the HDL part stands for Hardware Description Language, and the V stands for another acronym, Very High Speed Integrated Circuit. So everybody just says VHDL for simplicity. So it's originally it was a documentation language. So it was used to describe what the chip was supposed to do, and then later on they found ways to automatically translate the hardware description to actual hardware. So that's how the language is used today. And it was originally designed by the Department of Defense, I think around a large table, without having compilers first deciding what features should be in the language. So it's a very verbose language, so you have to type a lot to express very little. It's also very irregular, so that's what I meant by people sitting around the table to decide on the language, and somebody proposes one part and another proposes another part. So in some situations you have this syntax, and other similar situations you have a different syntax. And also most designers only use a small part of the language. So an example of the verbosity of the language, so there's the text on the left, and so the only thing this piece of code says is what I've drawn on the right. So there's a red box with a time constant of 50 nanoseconds that is connected to the blue box with a clock signal, and it also has 2 ports. So you can imagine how much typing is involved. Also, an example of the irregular syntax. So if you declare components, if you're typing words, you have to use semicolons, except for the last word, there you can't type the semicolon. And then, so this is the component declaration on top, and then if you instantiate it, you have to use a comma. So you can imagine how much mistakes you make there. Another shortcoming is that hardware design is very closed by nature. So it's totally different from software developers where there's open discussion. So there are very few communities where they work on open source hardware. So there are a few, but they have very little traction. I've seen some evolutions lately, but it's still the hardware community is a lot smaller than software, so that's also one of the explanations why there is no real critical mass there. Another issue is long feedback loops. So while I was doing my PhD, while I was near the end of my chip design, when I really started to hit the limits of what could fit into the chip, I knew that a full compilation, or a synthesization they call it in hardware, was going to take about 6 hours. So what I often did was work on it, and then before I go home, push the start button to come back the next morning to see that it failed after 3 minutes, because I used a colon instead of a semicolon. So that was so frustrating, and was such a waste of time that was really the trigger to start developing this. So I mainly said the bad points, but not everything is negative. So VHDL is a very robust way to design hardware. So, and you can build extremely cool stuff with it. So you can make your own processors. The Mars rover is filled with custom hardware. And the good thing is that a good IDE can solve most of the issues that the language has. So now I'm going to give a quick demo of what you can do with Sigasi today. So I have a small example project. It's actually the same as the one I used in the slides, and so you see that it should be very similar to what you're used to for Java development. So I guess most of you know JDT. So we also have the Project Explorer. We have an editor, an outline, and then we have some extra views that are specific for hardware design. For example, here on the right you see a hierarchy view, so that's more the boxes view where you have this chip with subcomponents that are interconnected, so you can have also view it in this way. And of course everything is interconnected, so you can use it to very easily navigate through your design. So that's actually one of the most important time savers for hardware designers now, that they can very easily navigate through their design. So here you have an instantiation of a block, and you can simply do open declaration and navigate through that code. So if you're used to Java development, you take this for granted, but for hardware designers this is something completely new, so it really saves that time. So in the editor, so it's Xtext based. So we offer almost all of the features that Xtext supports. So we have semantic highlighting. So for example, data types are colored differently. Here you see generics. It's kind of a constant. Clocks. The user can choose to give that different colors. So you have this tiny clues, like for example on the left side here you have a port, so it's light blue, and then on the right side you have signals. So without navigating around, you also have this extra information projected over your code, so that the idea is that the hardware designer should be able to focus on the creative part, so he should focus on hardware design and not struggle with the language all the time, because that was happening when I was doing hardware design. It's already complex if you just draw it on paper what you want to do, so if you also have to describe it, you really it really helps you with all the information you need is readily available. So also the outline is something we get through each text, not for free of course, but it really helped us in development. So a few extra things we have in there to help designers is with this new file wizard, for example, if you want to create a new file with template support. So you can say, okay, I want an entity architecture pair, finish. So lots of code generation that needs to be done can be done with autocomplete. So you have also static autocompletes to create a new constant, or also extra things. For example, these instantiations here, you can do that with templates, and it really saves you a lot of time when you're developing, because most of the stuff we can generate for you based on other information that's available in the project, so that both helps you type faster, and at the same time it makes it a lot harder to make errors. So the error I made the most before was, for example, if you change 2 ports in order, you immediately get this error message. So lots of errors you simply don't make anymore, and that's because of the shorter feedback loop, and that really improves your productivity. So that was autocomplete. Also, there are a few quick fixes. So if you have signals that you don't use, you can very easily remove them. Also, if you forget an input port, it gets an error. So all this kind of stuff really helps. Another thing that is a bit specific to VHDL is that VHDL designers like to think in columns, because before Sigasi was there, they were used to Emacs, and so the easiest way to create an instantiation was use this column select mode, and so copy here and paste there, so they really have a fetish for everything has to be vertically aligned. So the formatter we implemented supports this, so that we also take the vertical information into account. And also a very nice thing is rename support, so you can rename an element in line to, for example, give it more descriptive meaning, and also something that is very amazing for a hardware designer the first time he sees this. So back to the how question. So how did we go on with Sigasi? So we iterated a lot. So not only on the technology front, but also in business. So in the beginning, we only had an ID. So their question was, do we stay at the university or do we start a company? And so the advice we got there was start your company immediately, so the IP is in the company and you don't have to negotiate about that with the university afterwards. But the disadvantage was, of course, that we had nothing, so we couldn't sell anything. So the first years was splitting our savings in two, one part in the company and the other part, keep it apart to keep on living while we were building the company. So we went then from ID to prototype, started to go to the first users, get their feedback, work on the next version, until we had a basic product, and now we have the best product available to work with VHDL code. So one example of the feedback we got was initially we were really focused on refactoring. So we thought that would be the next thing, that's where the value of Sigasi will be. But the feedback we got from our users was, okay, that looks interesting, but we don't really understand it yet. But that autocomplete feature there, that's something we like. So that's why we shifted our focus on the editor to first give a tool that is usable for VHDL design instead of the 80s technology that they were using before. We also iterated on the company level, so we started with our own savings, but as soon as we got this basic product and the first customers, we could convince angel investors to also put their money in Sigasi, and that allowed us to go a lot faster and build our product. Also, the team grew, of course. We're no longer 2 people, but because we got this extra money, we could hire some people, and we have very good teams, so everybody's involved and working with great speed on the company. So we're built on Eclipse. The main technology we use is Xtext. So folding VHDL in an Xtext grammar was certainly not easy. It was actually very hard, but it's feasible. And other problems we had there was Eclipse is a very huge project, so it took a while to understand what all is going on, and there's still some dark issues for me in the modeling department, and business reporting is still a few dark areas, but the longer you're involved, the more you get to know things. Also, going to EclipseCon really helped for me. So the first version of Sigasi was not built on Xtext, but on an Antler grammar, and was at EclipseCon that I got in contact with the Xtext guys and was like, oh, we should have used that. So we switched. Also, we had struggles with the build system, and by discussions we ended up using Taiko really soon to help with everything. We also use Xcore a lot to maintain the ASD. We also start using Extend a lot, mainly for testing, but it's kind of contagious, so we start to use it everywhere now. And so we're mainly a consumer of Eclipse technologies, but we try to contribute back by submitting bugs. We also have fixed a few in Xtext and also did a few contributions to make Xtext faster, because hardware designs tend to be very large, and so we hit some limits of some performance limits of Xtext, where we then optimize Xtext to build in parallel and a few things like that. So we did not only have technical problems, we also have a few social problems. So the hardware community is very conservative, so they're very reluctant to change. And we heard all kinds of excuses why they have to stick to their Emacs way or Notepad++ way. Java is slow. I don't make syntax errors. This really looks great for beginners, but I don't need it. And yeah, sometimes it's funny and sad at the same time. Also, a few had bad prior experiences with Eclipse. So, on lots of those chips, you also embed your own processor, and lots of those design environments are based on Eclipse. But often it was an afterthought. Like, we also need an IDE, so we tweak Eclipse a bit and ship it with our tools, and so it was not always that stable, or the heap space was configured too low. So they all had, well, that's a reaction we often heard, like, oh no, Eclipse is way too slow, but I don't agree with that. And another big problem we had is that most of the people are easily convinced that a tool like Eclipse can really improve their productivity, but it's difficult to make that claim hard. So they can't just go to their manager and say, like, this will make me 2 times as efficient. So the value is clear, but it's difficult to quantify. And so our main approach to solve this issue is, we're all engineers, we're selling to engineers, and that makes the conversation easier, because we have experimented with real sales guys, but that's simply, that they don't work. So how do we market the tool? So we distribute it both as an RCP and as an Eclipse plugin. So most of the people in hardware design have no real experience with Eclipse, so for them it's way easier to have one-click download, one-click install, and then experiment with it, because very few already have an Eclipse IDE running where they can install it. So we have a free starter edition, so where they can simply download it, play around, and the starter edition is always free, and that has all features for small projects. For big projects, most of the features are turned off. And then also we have we distribute our plugin via the Eclipse marketplace, and that's starting to grow. So I checked yesterday for the last month, and about 20% of the downloads now happen via the marketplace. So that's nice. So what is next on our roadmap? So we further have to scale the business to continue to grow and go faster, because we have so many ideas what we want to do, but we're probably like everybody, limited resources. But what we're working on now is we do have VHDL support, but there's also a big other language for hardware design, Verilog. So we're working on that now. And we also want to add graphical features. So VHDL is a textual language, and it's a good way to define what you're doing, but it helps to have a graphical projection to visualize, like the boxes I've drawn. That really helps you to get an overview of what's going on. I definitely gonna look at serious demonstration I've got look at this morning. So as a conclusion, so for us, Eclipse is a great platform because it really allows us to focus on the VHDL specific part, and still we can offer our end users a complete solution. So that was a big argument for us. And so maybe getting started is easy is not the correct word. It was a difficult decision, but we made it. And you need a lot of patience and perseverance to go on in an adventure like that. So I hope my story was inspiring for you, and so if you might consider starting a plugin and how Eclipse can empower you to do so. Any questions?
Don't you have remarks about the file size of your RCP application?
So it's 100 megabytes.
Yeah.
So
do you have remarks from VHDL developers?
We had a few. So if they really are trying to defend Emacs, that the arguments you heard here there is like 100 megabytes for an editor, but it's not an editor. So there's Git support and there's all these other things. So and I don't know any computer nowadays that has a development machine for chip design where 100 megabytes should be a problem. Memory consumption is sometimes a valid argument, because if your designs get large, if the VM doesn't give back its heap to the OS, you can run into problems if you have to run other tools after our tool to do the synthesis, for example. There we got remarks that like, oh, is your tool consuming 700 megabytes of RAM? Is that necessary? But during the build it is, but afterwards we can give it back, but that depends on the JVM settings, of course.
I heard really closely your presentation, and I must underline your courage to do it. Because when I heard about the last tools produced from the big EDA companies, like Vivaldi series of Xeons, which is doing synthesis, analysis, and now high-level synthesis, and placement, routing, taking IPs at files, I can only underline that you have courage.
But we're not doing all of that. So we're really focusing on the engineer that is typing the VHDL. So for example, Vivado, that's a tool that's really focused on the chip, on the back end. So Vivado still has also VHDL entry, but that tool doesn't care at all where the VHDL comes from. So it just asserts that the code is correct, and if it's correct, it can translate it to a chip. So but our starting position is completely different, because when you're typing VHDL, it's most of the time it's broken. So, and you have to recover it and still give good support. And for the trend to higher level synthesis, so they're already working on that for a long time, but still VHDL is the language in between, so I think it will always be there. So, but I agree that eventually nobody, or almost nobody, will write it anymore. It's probably the same with assembler.
And we will always have to go deep for debugging purpose or some stuff like that. And many hardware engineers want to produce their own VHDL for some specific chips, but for state machines or for control rooms, computations, there are many integrated tools. I agree with value is very heavy, and for code completion and good code quality it's not so good. But people I'm talking with, which are hardware, say that they are not only coding VHDL, they are making the whole chain.
Well, and there, I think it was a very unfortunate choice of Xilinx to go for this exotic JIDE environment instead of using Eclipse as their framework, as an IDE, because it's true that people are starting to use more tools and more languages, and it would really be helpful if it was all in one tool, because now they have to switch everywhere, and the keyboard shortcuts are different, so if they would have just provided all plugins to offer those features inside Eclipse, it would be a lot more convenient for the end user to compose the workbench he needs.
If I look at those tools,
Sorry?
the GOAT, G-A-U-T, open source, high level synthesis, and they are moving to Eclipse. So maybe if you contact ship altogether, they'll benefit from it.